grounding conductor for service sized in accordance with National Electrical Code Table 250.66 can indeed be installed utilizing the Ufer method. The Ufer ground, also known as a concrete encased electrode, is a grounding electrode that is encased within concrete and is in direct contact with the earth. It's an effective means of providing a low impedance path to ground. When installing a Ufer ground, the grounding electrode, which is typically a length of bare copper conductor or a bar, is embedded within the concrete foundation of a building or structure. The concrete must be in direct contact with the earth. This intimate contact with the earth allows the Ufer ground to effectively dissipate fault current and provide a stable reference point for electrical systems. The size of the grounding electrode conductor is determined by NEC Table 250.66, which bases the conductor size on the size of the service entrance conductors. To determine the appropriate size of the grounding electrode conductor for service with 6 sets of 4-inch conduits, each containing 4 500 kc mil conductors, you would first calculate the total circular mil area of the service entrance conductors. Since there are 4 500 kc mil conductors per set, the total circular mil area for each set is 4 times 500,000 circular mils, which equals 2 million circular mils. With 6 sets of these conductors, the total circular mil area for all service entrance conductors is 6 times 2 million circular mils, resulting in 12 million circular mils. Once you have the total circular mil area, you can consult NEC Table 250.66 to determine the minimum size of the grounding electrode conductor required. The table lists various conductor sizes based on the size of the service entrance conductors. Find the range in the table that includes 12 million circular mils and then identify the corresponding grounding electrode conductor size. For example, if the table indicates that for service entrance conductors over 1,100,000 circular mils, the grounding electrode conductor must be a minimum of 3/0 American wire gauge copper, then you would use a 3/0 American wire gauge copper conductor for the Ufer ground. It's important to note that the grounding electrode conductor must be connected to the grounding electrode, which in this case is the concrete encased electrode. The connection should be made using a suitable connector listed for direct burial. The Ufer ground is considered a very effective grounding method due to the large surface area of the concrete that is in contact with the earth. This large surface area provides a low impedance path to ground, which helps to minimize voltage rise during fault conditions and improve the overall safety of the electrical system. The Ufer ground is often used in large commercial and industrial buildings, as well as in residential buildings. It is a reliable and cost-effective way to provide a solid grounding system. In addition to providing a low impedance path to ground, the Ufer ground also helps to reduce the risk of electrical shock. By providing a stable reference point for electrical systems, the Ufer ground helps to ensure that all exposed metal parts of equipment and appliances are at the same potential as the earth. This minimizes the potential for electric shock if someone comes into contact with an energized metal part. It is crucial to follow all applicable codes and standards when installing a Ufer ground. The National Electrical Code provides detailed requirements for grounding and bonding, and it is important to adhere to these requirements to ensure the safety and reliability of the electrical system. Also, it's important to remember that while the Ufer ground is an effective grounding method, it is not a substitute for proper bonding. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault current. Bonding helps to ensure that fault current will flow quickly and safely back to the source, tripping the circuit breaker or fuse and energizing the circuit. Therefore, it is important to properly bond all metal parts of the electrical system in addition to installing a Ufer ground. In summary, the Ufer ground is a concrete encased electrode that is an effective means of providing a low impedance path to ground. It is often used in large commercial and industrial buildings, as well as in residential buildings. The size of the grounding electrode conductor is determined by NEC Table 250.66, which bases the conductor size on the size of the service entrance conductors. When installing a Ufer ground, it is important to follow all applicable codes and standards and to properly bond all metal parts of the electrical system. Remember to consult the latest edition of the National Electrical Code and local codes for specific requirements in the jurisdiction. The Ufer ground, also known as a concrete encased electrode, offers several advantages over other grounding methods. Firstly, it provides a large contact area with the earth, resulting in a low impedance path for fault currents. This is because the concrete encasing the electrode has a significant surface area in direct contact with the surrounding soil. Secondly, the concrete helps to protect the electrode from corrosion, extending its lifespan and ensuring long-term reliability. The concrete acts as a barrier against moisture and other corrosive elements in the soil, preventing the electrode from deteriorating over time. Thirdly, the Ufer ground is relatively easy to install during the construction phase of a building. The electrode can be placed within the concrete foundation before the concrete is poured, making it a cost-effective and efficient grounding solution. Fourthly, the Ufer ground is less susceptible to damage from digging or other construction activities compared to other grounding methods that are buried directly in the soil. The concrete encasement provides physical protection to the electrode, reducing the risk of it being accidentally damaged or disconnected. Fifthly, the Ufer ground can help to reduce the risk of step potential and touch potential, which are hazards associated with ground faults. By providing a low impedance path to ground, the Ufer ground helps to minimize the voltage difference between different points in the ground surface, reducing the potential for electric shock. Sixthly, the Ufer ground can improve the performance of sensitive electronic equipment by providing a stable and reliable ground reference. This is particularly important in commercial and industrial buildings where electronic equipment is used extensively. When designing and installing a Ufer ground, there are several factors to consider. Firstly, the size and type of electrode should be selected based on the size of the service entrance conductors and the requirements of NEC Table 250.66. Secondly, the concrete mix should be suitable for direct contact with the earth and should provide adequate protection against corrosion. Thirdly, the electrode should be placed in a location where it will be in direct contact with the earth and where it will not be subject to excessive moisture or other corrosive elements. Fourthly, the connection between the grounding electrode conductor and the electrode should be made using a suitable connector listed for direct burial. Fifthly, the installation should be inspected and tested to ensure that it meets the requirements of the National Electrical Code and local codes. It is important to consult with a qualified electrical engineer or electrician to ensure that the Ufer ground is designed and installed correctly. They can provide guidance in the selection of appropriate materials, the placement of the electrode, and the connection of the grounding electrode conductor. They can also perform inspections and tests to verify that the installation meets all applicable codes and standards. The Ufer ground is a valuable grounding method that can enhance the safety and reliability of electrical systems in various types of buildings. By understanding the principles behind the Ufer ground and following the proper installation procedures, you can ensure that it provides effective grounding for your electrical system. Remember to always prioritize safety and consult with qualified professionals when working with electrical systems. Let's delve deeper into some specific aspects of Ufer grounding. The concrete that encases the grounding electrode plays a crucial role in the effectiveness of the Ufer ground. It's not just any concrete. It needs to be a specific type of concrete that is suitable for direct contact with the earth and that provides adequate protection against corrosion. Typically, a concrete mix with a low water to cement ratio is preferred. This type of mix results in a denser, less porous concrete that is more resistant to moisture penetration and chemical attack. The concrete should also be free of any additives or chemicals that could potentially corrode the grounding electrode. The thickness of the concrete encasement is also important. A sufficient thickness of concrete is necessary to provide adequate physical protection to the electrode and to ensure that it remains in direct contact with the earth. The National Electrical Code does not specify a minimum thickness for the concrete encasement, but it is generally recommended to have at least 2 inches of concrete covering the electrode on all sides. The location of the Ufer ground is another critical factor to consider. The electrode should be placed in a location where it will be in direct contact with the earth throughout the year. This means that it should be located below the frost line in areas where freezing temperatures are common. The electrode should also be located away from any sources of excessive moisture or chemical contamination. For example, it should not be placed near a drainage ditch or an area where chemicals were stored. The connection between the grounding electrode conductor and the electrode must be made using a suitable connector listed for direct burial. This is essential to ensure a reliable and long-lasting connection. The connector should be made of a corrosion-resistant material, such as copper or stainless steel, and it should be properly installed according to the manufacturer's instructions. The grounding electrode conductor should be sized according to NEC Table 250.66, as previously mentioned. The conductor should be run in a straight line from the service equipment to the electrode, and it should be protected from physical damage. The conductor should not be spliced or jointed between the service equipment and the electrode. Once the Ufer ground is installed, it should be inspected and tested to ensure that it meets the requirements of the National Electrical Code and local codes. The inspection should verify that the electrode is properly encased in concrete, that the connection between the grounding electrode conductor and the electrode is secure, and that the grounding electrode conductor is properly sized and installed. The testing should measure the impedance of the grounding system. A low impedance reading indicates that the grounding system is effective at providing a low impedance path to ground. If the impedance reading is too high, it may indicate that there is a problem with the installation, such as a poor connection or a corroded electrode. In this case, the problem should be corrected before the electrical system is put into service. The Ufer ground is a reliable and effective grounding method when properly designed, installed, and maintained. It provides a low impedance path to ground, protects against electrical shock, and improves the performance of sensitive electronic equipment. By following the guidelines outlined in the National Electrical Code and consulting with qualified professionals, you can ensure that your Ufer ground provides safe and reliable grounding for your electrical system. Let's consider a practical example. Suppose you are designing the electrical system for a new commercial building. The building will have a service entrance with 6 sets of 500 kcmil conductors per phase. To provide effective grounding for the building, you decide to use a Ufer ground. Firstly, you consult NEC Table 250.66 to determine the minimum size of the grounding electrode conductor. Based on the size of the service entrance conductors, you determine that a 3/0 American wire gauge copper conductor is required. Secondly, you specify a concrete mix with a low water to cement ratio and a minimum compressive strength of 3,000 pounds per square inch. The concrete mix should be free of any additives or chemicals that could potentially corrode the grounding electrode. Thirdly, you locate the Ufer ground in the building's foundation, below the frost line and away from any sources of excessive moisture or chemical contamination. The electrode is placed in a location where it will be in direct contact with the earth throughout the year. Fourthly, you ensure that the grounding electrode conductor is run in a straight line from the service equipment to the electrode, and that it is protected from physical damage. The conductor is not spliced or jointed between the service equipment and the electrode. Fifthly, you use a suitable connector listed for direct burial to connect the grounding electrode conductor to the electrode. The connector is made of copper and is properly installed according to the manufacturer's instructions. Sixthly, after the Ufer ground is installed, you inspect it to ensure that it meets the requirements of the National Electrical Code and local codes. You verify that the electrode is properly encased in concrete, that the connection between the grounding electrode conductor and the electrode is secure, and that the grounding electrode conductor is properly sized and installed. Seventhly, you test the impedance of the grounding system. The impedance reading is low, indicating that the grounding system is effective at providing a low impedance path to ground. Based on these considerations, you can be confident that the Ufer ground will provide safe and reliable grounding for the electrical system in the commercial building. The effectiveness of a Ufer ground can be influenced by various factors, including soil conditions, moisture content, and the presence of corrosive substances. Soil conditions can affect the conductivity of the earth surrounding the concrete encased electrode. Sandy or rocky soils tend to have higher resistance than clay or loam soils. Higher resistance soils may reduce the effectiveness of the Ufer ground by limiting the flow of fault current. Moisture content plays a critical role in the conductivity of the soil. Drier soils have higher resistance, while moist soils have lower resistance. Therefore, the Ufer ground will be more effective in areas with higher soil moisture content. The presence of corrosive substances in the soil can accelerate the corrosion of the grounding electrode and the concrete encasement. This can reduce the effectiveness of the Ufer ground over time. It is important to avoid placing the Ufer ground in areas where the soil is known to be contaminated with corrosive substances. Regular inspection and testing of the Ufer ground can help to identify any potential problems early on. The inspection should look for signs of corrosion, damage to the concrete encasement, or loose connections. The testing should measure the impedance of the grounding system. If any problems are found, they should be corrected promptly to maintain the effectiveness of the Ufer ground. The Ufer ground is a widely accepted and reliable grounding method, but it is not always the best solution for every situation. In some cases, other grounding methods such as ground rods or ground plates may be more appropriate. The choice of grounding method should be based on a careful evaluation of the specific site conditions and the requirements of the electrical system. Ultimately, the goal is to provide a safe and effective grounding system that protects people and equipment from electrical hazards. Remember that the National Electrical Code provides detailed requirements for grounding and bonding, and it is essential to follow these requirements to ensure the safety and reliability of the electrical system.